This section is a supplement to section 4.6, which talked about directional derivatives and the gradient. In this section, we consider the gradient and we take another look at tangent planes and normal lines and tangent lines to a particular level curve at a given point. This is not in your textbook, but I feel it's important for you to know, so I've included it in this supplementary section. Let me share my screen so we can get started. And by the way, it's super short. Let's start with a brief review of what we know about tangent planes and the gradient. We've seen different ways to write the equation of a plane. We began way back in chapter 2 with the general equation of a plane containing a point x naught, y naught, z naught, with the normal vector given by a, b, c. And the equation is here and labeled equation 1. It is the first component of the normal vector multiplied by x minus x naught plus b, the second component of the normal vector multiplied by y minus y naught, plus c, the third component of the normal vector multiplied by z minus z naught, set equal to 0. Then we learned about partial derivatives, and we discussed the equation of the tangent plane of a function of two variables at a given point in the domain, also being given by z equal f of x naught y naught, which of course is just our z naught, the partial derivative of the function with respect to x evaluated at x naught y naught in the domain, multiplied by x minus x naught, plus the partial derivative of the function with respect to y evaluated at x naught y naught in the domain and multiplied by y minus y naught. If you want to, you can write this in a somewhat simpler form, and just remember that you have to evaluate these at the point in question. In other words, you could write this as, whoops, changed colors there. Let's go back to black. Z equals z naught plus the partial with respect to x times x minus x naught plus the partial with respect to y times y minus y naught. And remember that you have to evaluate the two partials at the point coming from the domain x naught and y naught. Let's now think about the tangent plane at a level curve. Earlier in section 4.6, we learned that anywhere the gradient vector is, it will be perpendicular or orthogonal to the corresponding level curve at that point. Remember, the gradient always points in the direction of the steepest change in the dependent variable, in this case, z. It will always be perpendicular to the level curve at that point. Since the gradient vector is normal to the level curve given by z equals some constant at the point from the domain x naught y naught, or you can think of it as the ordered triple x naught y naught c on the surface, we can use it to write the equation of the tangent plane to the surface, where z is the value on the level curve using equation 1 above. Let's go ahead and take a look at the general formula for a tangent plane. Let's suppose that we have some function z of x and y, and we want to find the equation of the tangent plane at the domain point x naught y naught, which of course is x naught y naught z naught, or c, on the surface. In this case, we're going to define it implicitly by moving everything to the left side. This gives us the expression for the original function minus the variable z, which is our dependent variable, now equal to 0. Again, what we were starting with was z equal to some function of x and y, and we simply subtracted the variable z from both sides. However, this expression here, the function of x and y minus z, represents another function, but a function in four-dimensional space, which is a function of x, y, and z. And of course, it's set equal to 0. This gives us a function of 3 variables instead of 2. However, the 3D surface for the value where uppercase F is equal to 0 will be the same 3D surface produced by the original function of 2 variables in 3-dimensional space. Since we have this uppercase letter F as a function of x, y, and z, when we find the gradient of it, del F, we get the partials with respect to x, with respect to y, and with respect to z. However, remember that our equation was written in such a way that uppercase F was equal to the original function minus z. The original function is only a function of x and y. It does not contain z in it, which means that the partial of this equation with respect to z will always be a -1. And that means that we can find the partial of the original function with respect to x and the partial of the original function with respect to y. Let those be the first 2 components of the gradient of uppercase letter F, and let the third component be -1, the partial of uppercase F with respect to z. Then we can write the equation of the tangent plane to the surface at that particular point as the partial with respect to x evaluated at x naught, y naught times x minus x naught, plus the partial with respect to y of the original function evaluated at x naught, y naught times y minus y naught minus 1, which of course was the partial of uppercase F with respect to z, multiplied by z minus z naught, and set equal to 0. Now, in this case, note that A from the first equation that we had for the tangent plane is being replaced by the first partial evaluated at the particular point. B is being replaced, of course, by the first partial of the original function with respect to y evaluated at the domain point. And C, the third component of the normal vector, is being replaced by a -1. In this case, if we had this, we could write the equation of the tangent plane implicitly in this format. Implicitly simply means it's not solved for a variable, in this case, z, since it's in 3-dimensional space. We can expand this idea for a function of 3 variables, w, x, y, and z, and we would simply expand our definition to add in the first partial of the original function with respect to z, evaluated at the domain point, times z minus z naught, minus w naught, where w is now the independent, or rather the dependent variable. If the equation is not solved for z, and there are lots of occasions where it's either impossible or unpleasant in order to solve it for z, then it is an implicit function of x and y. In that case, you need to get the equation equal to 0 and set uppercase F to be equal to that expression. That means that uppercase F will be equal to some expression of x, y, and z, where you've moved everything in the original implicit equation to one side and you have 0 on the other. In this case, when we take the gradient of uppercase letter F, the expression that we have in the center is a function of x, y, and z. We no longer know that the derivative, partial derivative with respect to z will be -1. So this means that we have to write it as the partial of uppercase F with respect to x for the first component, with respect to y for the second, with respect to z for the third. However, this implicit equation defining some function z is a function of x and y is in fact what we have in that expression in the middle that we set uppercase letter F to be. In that case, the partial of uppercase F with respect to x is equal to the partial of the original with respect to x. and the same for the y and the z. In this case, note that the last one is no longer -1 because we hadn't had the original equation solved for z. In this case, we can go ahead and write the implicit equation of the tangent plane to the surface at the point as the first partial of x, or first partial with respect to x of the original function, times x minus x naught, plus the first partial with respect to y at the point, times y minus y naught, plus the first partial with respect to z at the point, times z minus z naught. Now let's go ahead and take a look at an example. In this example, we're given an ellipsoid. Now, an ellipsoid, of course, is like a three-dimensional space. It's a three-dimensional surface that has traces that appear to be ellipses. When we look at this equation, note that we have x squared, y squared, and z squared. It is possible to solve for z, but it would require taking plus or minus the square root of everything else. We're going to work this using the implicit equation, x squared plus 2y squared plus 3z squared equals 18. What we want to do is find all the points where the tangent plane to this ellipsoid is parallel to the plane given by 2y minus 2x minus 6z equal to 0. The first thing I want to do is go ahead and rewrite the plane that the tangent planes are going to be parallel to in the normal order with the x term first, y term second, and z term third. That's because this is a plane and I need to have the normal vector. This gives me -2x plus 2y minus 6z equals 0. The next thing I'm going to do is pull off the coefficients, and that will give me a normal vector to that plane, which is -2 to -6. Any multiple of this will work as a normal vector to that plane. We could have divided everything by 2 and used -1, 1, -3, or divided everything by -2 and used 1, -1, 3. All we need is a vector that is normal to the plane, because if the tangent plane is parallel to the plane given by the equation, then their normal vectors must be parallel as well. For the tangent plane, this means that our normal vector for the tangent plane is some multiple of that vector, -2 to -6. And I chose just to leave it as it was for ease of explanation. However, the gradient is also normal to the level surface. We know it cuts across the level curve at a 90-degree angle. So it has to be normal to the tangent plane at that point, which means the gradient of the original function of x, y, and z has to be some multiple of -2 to -6. Now, the gradient can be found from the original equation where we've moved everything to one side. Let's go back to our original equation. Up here, we have x squared plus 2y squared plus 3z squared equals 18. Move the 18 to the left so that it's equal to 0. Your expression for uppercase F then becomes the following expression. It becomes x squared plus 2y squared plus 3z squared minus 18, and yes, it's equal to 0. It's sort of like a level surface. Well, it is a level surface where the value of uppercase letter F is being set at 0. In this case, to find the gradient of uppercase F, it's essentially the same as finding the gradient of the original function. In this case, it's defined implicitly, not solved for z. To find the gradient, we simply find the first partial with respect to x, then y, then z. This gives us 2x for the first component, 4y for the second component, and 6z for the third component of our gradient vector. You can see that written here in the center. When you're looking at this, then we know that the gradient of that curve must be some multiple of -2 to -6. We want to find what values cause that to happen. At what points on the ellipsoid does that occur? We're going to let ABC be an ordered triple that represents the point or points where the tangent plane is parallel to that given plane with normal vector -2 to -6. In that case, then we can substitute A, B, and C in place of X, Y, and Z to get the equation, the vector 2A, 4B, 6Z equals some constant K times the vector -2, 2, -6. This gives us 3 equations and 4 unknowns. We have A, B, C, and K as unknowns. This only gives us 3 equations, so we'll not be able to solve it completely at this point. However, we can set corresponding components together so that 2A must equal -2K, or A is the opposite of K. 4B equals 2K, so B is half of K. And 6C equals -6K, so C is also the opposite of K, meaning that A and C must be equal to each other. Any point on the surface given by the relationship -K, K divided by 2, -K, is going to have a tangent plane parallel to the given plane. Because it has to be on the ellipsoid, it has to solve that equation for the ellipsoid. We can find the value of K by substituting into the equation of the ellipsoid. The equation of the ellipsoid is given again up here at the top. Remember that we're replacing X with -K, Y with K divided by 2, and Z with -K. When you square the terms and distribute, you get an equation in K squared, which gives you 9/2 K squared equals 18. Dividing by 9/2 or multiplying by 2/9 gives you that K squared is 4, which means that K could be 2 or -2. Then we use our relationship again. Let's suppose it's 2. If K equals 2, then my relationship is -K, so I get -2, half of K, so I get 1, and again, -K, so I get -2. If the value of K is -2, I get the ordered triple 2, -1, 2. Let's take a look at what this looks like on CalcPlot 3D. On CalcPlot 3D, what I did was I first graphed the ellipsoid, which is in this equation here. I graphed it as an implicit surface in the select box. Then I graphed the 2 points that I found, which were 2, -1, 2, and -2, 1, 2. Then I graphed the plane where the tangent planes to these points are going to be parallel. The plane 2y minus 2x minus 6z equals 0 was also defined as an implicit equation. It's the one you see cutting through the center of the ellipsoid. You'll see the 2 points here in yellow. Then what I did was I found an equation for the plane. I have a normal vector. It's -2 to -6. Or I could have used something similar, different. And then I put it through my point, depending on what the point was. Looks like I've got the 2 different points here. So -2, -2, -6. Once I have this, notice that the 3 planes are in fact parallel. Also note that CalcPlot 3D tries to show things in terms of a 3-dimensional view. It's actually a little bit more apparent that they are parallel when you tilt them ever so slightly. Let's move on now to example 2. Example 2 is a different ellipsoid given by 2x squared plus y squared plus 4z squared equals 42. We want to find the implicit form of the tangent plane to the ellipsoid at the point 1, negative 2, 3, which is on the surface of the ellipsoid. Follow the process that we followed in the last example, where we found a function, uppercase letter f, based on taking the original equation, which defined z as an implicit function of x and y, and moving everything to one side so we had 0 on the other. And find the gradient of that, which will give you the partial with respect to x, y, and then z as its 3 components. And then you can write an implicit equation of the tangent line using the formula below that. Go ahead and pause the video now to work it out, then turn the video back on, and we'll compare our work. First, we define uppercase letter f to be a function of x, y, and z, but we take the level surface where that is equal to 0. This becomes 2x squared plus y squared minus 4z squared minus 42. Then we find del f, the gradient of that function. This gives us the vector 4x, 2y, 8z. Next, we want to evaluate this at the point 1, negative 2, 3. This gives us the gradient vector at that point, which turns out to be 4, negative 4, 24. Note that any multiple of that would work as well. What we simply need is something that is normal to the tangent plane. Then we can use the equation for the tangent plane to replace each piece and evaluate what the implicit equation of the tangent plane is. This gives us 4 times the quantity x minus 1 minus 4 times the quantity y minus a negative 2 or plus 2 plus 24 times the quantity z minus 3 equals 0. You could divide all the terms by 4 to simplify it, and you could, if you want, distribute all of the factors and obtain the equation x minus y plus 6z minus 21 equals 0. This is an implicit equation for the tangent plane because it's not solved for z. However, in its third form, it would be rather simple to go ahead and solve for z. Let's take a look at what this one looks like out on CalcPlot 3D. On CalcPlot 3D, we were given an ellipsoid and the point 1, negative 2, 3. And then we wanted to find the tangent plane where this was touching that point. If you rotate, you'll be able to see that, in fact, we do have the tangent plane. It's a little hard to get it right on, but oops, I had it for a moment and then it twisted. There is about the best I can do. And you can see that it is barely touching the ellipsoid at that point. We now want to turn our attention to the 2 lines associated with a level curve. These are lines, not vectors. The gradient is a vector which points orthogonal to the level curve at any point. We want to find the line that lines up with the gradient vector, but extends in both directions forever. For this, we'll need a space curve where we define it parametrically. When we do this, we'll take the position vector, standard position vector of the point at which we want to find the normal line. The normal line is the line that is normal to the level curve at that point. It aligns with the gradient vector. Then we add to that the parameter t multiplied by the gradient at that point. Because the gradient aligns with that line, we can use the gradient vector as our vector in the parameterized equation for the space curve. Let's now go ahead and take a look at example 3. In example 3, we want to return to the ellipsoid from example 2, same equation, and we want to find the equation of the normal line at the same point. To find the equation of the normal line, we're going to define it as a space curve, r is a function of a parameter t. We give the standard position vector of the point, which is the vector 1, -2, 3, plus the parameter t multiplied by the gradient vector. In the previous example, the gradient vector was 4, -4, 24. We can use this or any multiple to get the equation of the tangent line. When you graph this, make sure that you set the parameter t to extend in both directions for quite a ways. Probably -10 to 10 will work. You could also write this in a combined form by simply adding together corresponding components. This would become 1 plus 4t, -2 minus 4t, and 3 plus 24t. You can enter this into CalcPlot 3D on the previous graph in order to see what it looks like. Let's take a look at it. When we do that, you can see the tangent plane, and and it moved again. Rats. Let's see if I can get it a little better. And it's not cooperating. There, don't move. Okay, now that I have it there, you can see that the tangent plane is tangent, and notice that the normal line, which is here in black, is normal to the tangent plane, coming off at a 90-degree angle. And again, you can see that it is at a 90-degree angle if we rotate it. Let's now take a look at the equation of the other line we might be interested in if we're talking about on a level curve. And this would be the tangent line. The tangent line is a little bit more challenging to do, and I've split it into two parts. One, if you have an explicit equation in terms of x and y, where you have z equals, then your equation will be using this here. This is because the dot product of two vectors will be 0 if you swap their coordinates in the vector and negate only one of them. If you do that and you set the last coordinate to be 0, since this is solved for z, then this will give you an equation of the tangent line to the normal curve at that point. In the examples we've done, however, our equations have not been solved for z. They've been implicit equations of z as a function of x and y. In that case, what we need to do is take essentially the same thing, but set the z value to be at that level curve. In other words, it will take on the z value of z naught, whatever that happens to be. This is the equation you use for an implicit equation of two variables. Let's now return to the ellipsoid from example 2 again and find the equation of the tangent line at the same point. Because ours is an implicit equation of z as a function of x and y, we'll want to use this second formula. Go ahead and pause the video, compute the partial with respect to y and x, negate one of them, and form the vector valued function for the tangent line at that point. Then turn the video back on and we'll see if we match. Because our equation was defined implicitly, we want to use the form of the vector valued function you see here, where the z value is set to be the z value at that point, in our case 3. The partial with respect to x of our original function is 4x. When we evaluate that at our ordered triple 1, -2, 3, we obtain 4. The first partial with respect to y is 2y, and evaluated at our point gives us -4. Now, in order to form the equation of the tangent line to the level curve at that point, I take the standard position vector for the point and add to it the parameter t multiplied by the value of the partial with respect to y, the partial with respect to x, and the z value at the point, with one of the partials negated, but not both. This gives us two possible values. The vector 1, negative 2, 3 plus t times the vector negative 4, 3, or the vector 1, negative 2, 3 plus t times the vector 4, 4, 3. In both cases, the 3 stays the same. Let's take a look at what this one looks like out on CalcPlot 3D. When we look at this one, the first image that I have for you is the image of the contour plot. I told it to plot one contour line at the value of 3. That gives me a z value of 3. You can see the point 1, negative 2, 3 in yellow here. You can also see the normal line, which I previously graphed in black, and you can tell that it is normal to the curve at that point. Then I graphed what we found to be the equation of the tangent line. Notice it is tangent to the level curve at that point. And then we can take a look at it back out in normal 3D mode, where you can see this view of it here. Now you may be wondering how I got the contour line to show up. When you define a function implicitly, CalcPlot 3D will not do a contour line. I knew it was on the upper half of the ellipsoid, so what I did was wrote an explicit equation for z, which is equal to the square root of the quantity 42 minus 2x squared minus y squared, all divided by 2. When you take the square root of the coefficient of z, which was 4, you get 2. This gave me an explicit equation, which opened up the possibility of doing a contour line. And then I was able to do the contour line when the z value is 3. You can tell from this picture that, in fact, the tangent line and the normal line are orthogonal to each other. And it's a little hard to tell, but in fact, the tangent line lies within the plane. I don't know if I can get it any better straight on. I don't think so. You'll just have to take my word for it. I hope that this has helped you to understand how to relate the gradient to the equation of a tangent plane at a point, or to the equation of the normal line or the tangent line. These are important skills to be able to find these things, and they didn't exactly appear in the textbook, so I added this section just for you. In our next video, we'll be looking at maxima and minima problems, finding maximum points and minimum points on a surface compared to the points nearby. Join me for the next video in this series.